Yaskawa. You're watching the IEC 61131 Basics video tutorial series. We'll examine the topic of multitasking in the IEC environment using MotionWorks IEC. Hi, I'm Matt Pelletier, and in this section we'll make some significant changes to the parking gate control example so that we can see how to create a new task, what the different task types are all about. We'll add a system task, default task, and slow cyclic task. Then once we have all these tasks running on the PLC simulator, it will make sense to look at the watchdog setting and other properties. Okay, as an overview of multitasking before we get into the software, let's understand that there are 4 task types. Those 4 types we will see are system, cyclic, default, and event. You can have, with Yaskawa controllers, up to 16 tasks. The number of simultaneous tasks is up to the vendor. The task interval can be set, and that lowest interval, or scan time, depends on the PLC. So here for this class, we're using the simulator, and it is set for a lowest interval of 10 milliseconds. Our MP2000 IEC series controllers will do as fast as 1 millisecond, and the latest at the time of this video are the MP3000 IEC series, which can go as fast as 0.125 milliseconds. There's another concept, which is that of task priority. If you have multiple tasks, which task can interrupt the other? That's the priority, where 0 would be the highest or first done, and 15 is the lowest priority, running last. And remember what we learned before when we studied I/O was that task execution involves reading inputs, the %i, variables, solving the program, POUs, and then ending that task by writing the outputs. So when we have multiple tasks, we'll also have to pay attention to logically put the input and output variables to write to the task that is appropriate. Okay, so why don't we go to our project and insert a new task by right-clicking on the task folder and choosing Insert Task. So here we are in our project. Debug mode is off. And I will insert in the task list a new task, insert task, and before we type the name, let's look at the different types of task. We have default, cyclic, event, and system. Starting at the top, default. The default task executes after all other tasks complete. This is the task for an example of code you might put in the default task is perhaps a mathematical equation that does not have to complete at any particular time, and it can be worked on, so to speak, in the background. Another word for the default task is the background task. The next one down here was cyclic. Cyclic is the task that we're used to. It's your normal scanning task you'd find in a PLC. It repeats at a given interval. They use the term interval. And so the idea is to have several cyclic tasks, and we'll just make 2 here, a slow one and a fast one, a slow task and fast task. The slow task can be used for non-time critical operations, such as monitoring or user interface. And the fast task at a fast interval in order to accurately control machine I/O and motion. And we'll see here in a bit when we choose a cyclic task, we'll also have the priority. Priority applies to the cyclic tasks. The next task down is event, and the event is a task that will execute one time. Does one run through the code when a certain condition is met. Interestingly enough, the event task is not often used in motion control, and the reason is that it's somewhat limited with the fact that there is only one scan. because if we are controlling motion, we'll often need to have function blocks, and most function blocks take more than one scan to complete. So since you can't put a function block into an event task, it's often not very useful to have an event task to handle your interrupt events. Instead, we would use a cyclic task and scan for those events. Very similar to the event task is the system task, but this task will execute one time when the system reaches a particular state. And the most commonly used states are the warm start state or the cold start state. And so let's have the system task be the first task that we create here. And we'll create one for warm start and one for cold start. You could also consider several different errors in here, and if you want to see what the rest of these mean, you can look at the help. So we wanted to create a system task called warm. So I'll start with the name, warm, and we'll choose the task type as system. And when you click OK, you see that it has the warm, and the other SPG numbers are listed here. And I had mentioned you could find the help here to read up on the other, what they call SPG numbers here. What you do here is go to help, and then in this table here it says SPG number, and there is a link here called system programs, and this tells you a little more information about what each of these SPG numbers mean. So I'll leave that to you on your own. We are going to use warm start and click OK. And then you might think, okay, well, let's download changes with this. And right away, it seems like nothing happened because I have an error. The error is missing program instance in resource configuration resource task warm. So here's our task warm. There is no program instance. So we will need to make a program instance like we had done here for the other program POUs that we created. We had an instance for them. We don't want to run the same instances again in warm. Instead, we'll make a new one. So let's go to logical POUs and insert. It'll just be blank for now. Let's call it init. You'll often initialize items in the warm start task. So it'll be blank for now, and I want it to be structured text language. Okay. So now I have the init POU, and now we can insert the program instance. Let's do insert program instance. And I'm going to call this one init underscore warm. You'll see why here in a minute. The program type will be init. Now, normally I would match these names, but what I'm going to do is we'll also create a cold start task to run the same init program. This is one of those cases where you might want the program instance running in two different tasks, since the two tasks will never run at the same time. So I'm calling this init warm, and once there's a program instance, then this error will go away with the download changes. And it says download changes not possible, and this is another one of those basic hardware changes. Creating a new task cannot be added while the processor continues to run. And so instead, you do a stop and download what's been compiled. And now when we do a warm start, it will run the code, which is blank. It will run it, and we're running again. So what I would like you to do here, try to do this on your own, is could you do the same thing now? I ran through how to do the warm start task, and I hope you were following along with me. Now could you create the cold start system task? And we've already created the blank structured text POU named init. So you can add another instance called init cold of the same program init. So take a couple minutes here and see if you can go through that and do that on your own. And you can pause the video, and then I will show how to do it. Okay, to insert the cold task is very similar to the warm. Insert task, call it cold. The task type was the system task, and instead of warm, we'll choose cold. Click OK. And there it is, but with no instance in it. So we'll insert the program instance, call init underscore cold, program type init, and just to be sure I have no mistakes, I will make again. All right, it looks good. So we can see now we're starting to get multitasks within this task folder. Next, we will create the default task, and I would like you to name it background with a 500 millisecond watchdog. We'll look at that a little bit more as we get going here. And then create a blank structured text program POU named lowest priority so that this background task does have something to run even though it's empty for now. So please try to do this on your own. You can pause the video now and I will give the solution. Okay, here's adding the default task. Right click, insert task. We wanted to call it BCKGND. There is a character limit on that. The task type is called default. We click OK. We'll leave the watchdog time at 500. And I wanted a blank task in there called lowest priority. So let's create a program called lowest priority. We have a couple blank program POUs for now. But we'll put an instance of lowest priority into the background task, insert the program instance, lowest priority, and of program type, lowest priority. Okay. And once again, make to be sure there's no problem. Looks good. We do have some warnings now, and these warnings are that variables have never been used and worksheets are empty, these two particularly, and we'll be able to address these at a different video. Just leave those here for now, no problem. Now let's create a cyclic task named slow. And remember, why have more than one cyclic task? The answer is to optimize your code execution. Yes, our example is very simple. There's really not a lot of optimizing to do at this point, but to put the good practices into place, remember it's your critical POUs that should be in the fast task, those POUs that control motion and machine I/O, and non-time critical POUs in the slow tasks, things such as user interface. And as you want higher and higher performance, you'll have to have different levels of cyclic tasks with different cycle times. So we're going to create a slow task. Let's do that now. In the tasks folder, insert task, call it slow, and it's a cyclic task. Looks like it knows that we can't have another default task. Okay. And for cyclic tasks, you're presented with the interval, the priority, the watchdog time, and you can read the help to find out about these stack end options, which we usually don't touch. The three important ones here, interval, priority, and watchdog. So how do you set these? Let's set the interval time to 200. That's your choice. The watchdog time should be set equal to the interval. And then the priority. Well, what priority should this slow task be? Let's use priority 7. Why 7? Well, remember how high the priority can go? What's the last task to be executed? If you recall, we can have up to 16 tasks, and the priorities go from 0 to 15. And so 7 leaves room for a higher priority task, some maybe medium or medium high, and at the same time there's a lot higher values here, meaning lower priority. We could have 8, 9, 10 up through 15 if we had even slower tasks in the future. So it's a good number there in the middle of the range. So let's set that up, 200, priority 7, watchdog equal to that at 200, and click OK. And when you're considering the task priority, remember that the tasks are executed sequentially in the order of priority, where task with priority 0 is first and 15 is last. The software will at this time allow you to enter as high as 31. As we say here, don't do it. Your controller has other tasks which you don't see for taking care of itself, and you want those to execute before the controller internal tasks. So please use 15 and lower for the values. And if you want a way to think of prioritizing tasks in the controller, it's very similar to something like prioritizing office work. So if you think about it, phone calls usually would be the highest priority. Somebody calls you, you typically stop what you're doing and answer the call. And somebody comes by and you get an email or somebody wants a report. You don't typically hang up the phone call. You would finish the phone call before going on to other tasks. You may prioritize emails, have to be responded to in a timely fashion, and depending on what you do, there may be daily or weekly or monthly reports or yearly goals, things you have to do less frequently. You don't typically work on first. As we say here, you wouldn't first work on your yearly goal and be sure you get that all done and not answer any phone calls or emails while you're trying to get that yearly goal done ahead of time. So in a similar way, the processor really is not doing more than one task at a time. It's just moving between different tasks and prioritizing which tasks to do first. Another field jumping down here was Watchdog Time. This is the maximum time for the task to complete. And we had set that the same as the interval. And what this means is that if there's so much code that it cannot process and figure it all out in the Watchdog Time, then the resource will open up and you'll get an error and it'll tell you that the watchdog was exceeded in a particular user task. When this happens, you need to analyze what's going on. You may just need to increase the watchdog time and interval together, or it may be that your code has some type of infinite loop in it, making it run too long. The next thing that we will do is let's right-click on the existing task and change its settings. Let's change its settings to have an interval of 20, priority 0. This is the first task that should run, with the watchdog time matching here of 20. So here's the existing task. Right click on it. We have the settings. It was running at 100. We are going to set this to 20. Leave the priority at 0 and the watchdog then also to 20. Okay. And it also can be useful to change the task properties of any of these tasks, such as the name and the type of task that it is. So if you right click on the task and choose properties, let's do that. And let's call this task fast instead of just task. That way we'll have slow and fast. So right click on the task, choose properties, and let's change it to fast. You can see here you can go back and change the type. We'll leave it at cyclic. Click OK. And now I'd like to show you another option, which is instead of creating another program and inserting an instance, let's move the money POU from the fast task to the slow. You simply drag and drop. So I'll take money and drag it into the slow task. And why did I do that? Well, is it really necessary to calculate the amount of money in taxes every 20 milliseconds? Probably not. In reality, is it really necessary to check the sensor every 20 milliseconds? Also probably not. But let's go along with this. We know that we're controlling motion and I/O in the fast task, and we then can have the ability to do that. But this calculation that's just kind of for our information can be done at the slow task, so we're not bogging down the controller and the processor with this operation. So do you guys remember at this point, what is the slow task cycle? If you don't remember, right click on the properties and look. What's the fast task cycle? Right click on those properties and look there too. Actually, it's settings, not properties. And then to answer this one, which POU can be executed at a slower cycle? Oh, I think that money could be executed at a slower cycle. So now we have this multitask project. We should make and run this. So I know from before that download changes won't work when I make changes to the tasks. So I did a make, and now I will do stop, download, download, and we get this message. It says the cycle time of the fastest cyclic task is 20 milliseconds. The system tick frequency is 10 milliseconds. It is recommended to have a cycle time at least 4 times larger than the system tick. Do you want to proceed? What does this mean? There is something called the system tick in any IEC controller. And your task cycles should be set to an interval that is an integer multiple of this system tick. By the way, in the MPIEC controllers, the system tick is the motion network, the Mechatrolink network over which we communicate to our servos and network I/O. And we could see the system tick by looking at the info button on the resource tab. Generally speaking, this warning is fine, and you can just click OK to accept it. So I'll click yes to proceed. And here's the info button. It says right here, system tick 10 milliseconds. And this is based on the simulator. Okay, I know there's a lot of other data here, and we'll warm start the controller. So let's take a look now at these cyclic tasks and the system tick and see how this interacts with each other. The idea here is that one task can interrupt another, and the critical fast tasks will interrupt non-critical slow tasks. So let's just pretend that for now the fast task takes a certain amount of time. I'll just put a number on it of 0.7 milliseconds. And slightly different than what we have here. Let's say we have 2 milliseconds, and we set the priority to 0. And let's say that the slow task can execute code in 3.5 milliseconds, and that we've set the interval to 8 with priority 7. So similar to what we have, but a bit faster. And then the system tick, the system task is hidden in the system operations, and for a MPIEC controller, it would be the Mechatrolink network update. And our system tick in a real controller is typically around 2 milliseconds for the MP2000 IEC controllers. And as an example, the actual duration of this system tick is very short, maybe 0.2 milliseconds in the MPIEC controller. So you see what's going on here is every 2 milliseconds from the system tick, the system interrupts to do its business. Maybe if there's a servo system out there, it's managing that network. And then we have also set to 2 milliseconds a fast task. So the fast task is operating, it does the entire contents of the fast task. And you see that when the fast task is complete, the slow task starts, but it doesn't have time to finish before the system has to interrupt and the fast task executes again. And then the slow task can continue, and this happens until at the very end the slow task does eventually complete. And when all of the cyclic tasks have completed, that is when then the default task can run and do as much as it can get done until this whole sequence starts over again, where we do the fast and slow. So that this just goes on and on and on and on and on continually while the PLC runs. So I have a couple questions on here to try to put this together. One question is, how long does it truly take the slow task to execute? We said the code could execute in 3.5 milliseconds, but it's certainly taking a lot longer than 3.5 milliseconds. And if you look at it here, it might be, looks like it's taking almost the entire 8 milliseconds, maybe a bit less, like 7 milliseconds in this example. And another question I have here is, what important item is missing from the timeline? We've seen a timeline in a different video. Do you remember what we showed in a timeline that was similar to this in a previous video? If you're thinking the input reading and output writing, you are correct. The inputs and outputs also need to be read, and remember the inputs and outputs are assigned to a specific task. So they could have a read at the beginning and a write at the end of the fast if that particular input module is tied to the fast task, or it could be at the slow, read at the slow, and write at the end of the slow if the I/O for that module is configured for the slow task. But some of you are probably thinking, okay, well, how can I monitor what's going on in my controller and see what these times are, see what the fast time is as the code runs? because it's not going to stay the same. It's going to change depending on what's being executed at the time. While that is true, unfortunately, with the simulator, we cannot monitor how much time it's taking. It's just a feature that's not supported. However, please know that for the MP IEC controllers, there is a variable called high-res task timing info array, and you would see very easily in here the number of microseconds even that the current duration is for a particular task, the minimum and maximum, and the priority and period and watchdog. So when you get to a real controller, this is when it becomes more important. And yes, you can monitor this, and this becomes a very important part of tweaking your system and making your application run to the maximum performance possible. So I wanted to entertain the idea here of interval and priority and think about what happens if you have the incorrect priority. We've seen this happen in the field where customers don't understand priority and they maybe set every task to 0, or they have them flipped around thinking that 0 is the last. If we were to set the fast task to priority 1 and the slow task to priority 0, what would happen? It would work like this. The system tick can't be stopped, but we'd first work on the slow task. It wouldn't be done. We then continue working on the slow task, and really by the time that this happens, you'd already have a watchdog on the fast task because the fast task did not get done in the 2 milliseconds that it needed. It maybe could have gotten done after a couple scans here, but this is not acceptable, and you get a watchdog. And so the problem here is not that you have too much code in the fast task. The problem here is that the priority is set wrong. And so I hope this is a good illustration to show how we need to pay attention to the interval and the priority when we're setting up multiple tasks when using IEC 61131. Now, I had mentioned that the I/O configuration was important, and when we have multiple tasks, it is important that the I/O be assigned to the task in which they are used. You assign the I/O to the task in which it will be used. So where are our I/O variables being used? I'll answer that for you. They are being used in the fast task, right here in I, PCSim, and Q, PCSim. We have only one input and one output module. And so remember how to monitor that. You open up the I/O configuration, and each module will have its own line here with the address range. We have just one, but each module will have this, and you go to the properties and you can see here the task that it's assigned to. And now that we have more tasks, there's a lot more options and a lot more possibility to get it wrong. So you definitely want your I/O assigned to a cyclic task, and if you're using it in the fast task, as we see we are here, you want to update it in the fast task. So we can cancel out of this. And here's an illustration, a kind of a timeline here of what would happen if you have your I/O configuration assigned to the fast task. We have the system tick. You then read the inputs assigned to that task. Execute the task. The task is complete. You immediately write the outputs to the output module. And then there may be other tasks like slow or medium, or there may be other things going on. But as far as the input and output, that is done. You wait until the task starts again, and this repeats. So now I want you to think about this second item. What if the I/O configuration has assigned an input module and output module to the slow task? Where exactly on this timeline would you read the inputs and write the outputs? And I'll pop in the answer here. You would read the inputs when the slow task starts, right before it starts. The slow task starts, and not until the slow task completes would the outputs be written. So all these interrupts happen during that time. So now think about this question again. What if an input changes state rapidly and you've assigned the I/O to the slow task? If you have many input changes, they would not show up in any of the tasks. It would read it once at the slow task, and any changes that happen during that slow task would not be used. So this is not to say that you always should assign your I/O to the fast task. What it is to say is that if you're using the inputs in your code in the slow task, assign them to slow. If you're using the inputs in the fast task, assign them to fast. There's no reason to update inputs quickly and then only use them at a slow rate. If you do that, there is the opportunity that the input would change state during the execution of the code, and that may not be what you want. And so here we have one final master example of task execution in an MPIEC controller, where we use Mechatrolink as the system tick. We have a startup task, maybe that's the warm start. We have a fast task happening looks like every 2 system ticks in this case. We have a medium task that starts and ends. Looks like every at this time interval. And we have a slow task assigned to yet another even slower time interval. And you can see that even though there's not a lot of code in the slow task, it gets interrupted so much that it does ultimately take quite a bit of time to complete. Also indicated on this diagram, we have inputs being read and assigned to the medium task and outputs written. So you can see how that input reading and writing, if it's assigned to the medium task, will operate in time in this way. So thank you for your attention. This is how IEC controllers work when using multiple tasks.